mathematical connections. So here we want to see a transformation of the function f of x into the function g of x. So the example says, describe half the graph of g of x that is equal to 3 times 2 in exponent 2x plus 1 minus 3 compared to the graph of the function f of x 3 times 2 in exponent x. So if we are looking first at the coefficient 3, that signifies the vertical stretch or compression. Now they are the same, so the function g of x doesn't experience any vertical or stretch or compression. But if we are looking here, we have a 2x, and here we have a 2, the base is the same, 2. But what's happening here with the exponent, here I have x, here 2x. And this 2 here, because it's a greater than 1, it means I have a horizontal compression. If this number is less than 1, we would have in this function here, comparing to the parent function, we would have a stretch, horizontal stretch of the function. But because this is 2 is greater than 1, so here we're going to have a horizontal compression. So now here is just x, but here we have 2x plus 1. And because we have a positive 1 here, 2x plus 1, it means that the graph of the function f of x is going to translate horizontally at least for 1 unit. But it depends, because it's not everywhere the same gap between those two functions is going to change, as we are going to analyze. And third, in the third, here I have minus 3 in g of x, and here I don't have anything. So this minus 3 here signifies that we're going to have a vertical translation of the graph of the function, parent function, into 3 units vertically down. So let's go now and let's analyze piece by piece. And now if we go in a horizontal compression, as I mentioned before, because here was in the parent function 3 times 2x, and here it was a 2, so that's how we're going to see geometrically this kind of compression. So the red graph of the function or parent function is going to compress horizontally in this side. So this is how geometrically we can see it. And now horizontal translation. Here was 3 times 2 in exponent x, but now the green function is y is equal to 3 times 2 in 2x plus 1. And this 2x plus 1 tells us the parent function is going to translate horizontally, but we don't know exactly. For example, if you look at the interception point here, and at this point here is going to be exactly 1 unit. This one that signifies 1 unit is going to go to the left. But as we are going further and further up, this gap between the red function and the green function is going to increase. But if we are going down, the gap between the red function and green function is going to decrease. So it's not a uniformly in a whole space here, but it's just in this number 1 signifies just wherever is, for example, to the interception point, those two can have just 1 unit is going to translate horizontally to the left, 1 unit. Now let's go back here, the vertical translation. How is going to be the vertical translation? Because let's say before we had the function in this position, 3 times 2, 2x plus 1 in exponent. But if we are adding minus 3 in the function, this means we have a vertical translation 3 units down. So this vertical translation is going 3 units down, and whenever was the horizontal asymptote, which was y equal with 0 here in the green function, but now because we have this minus 3, and the horizontal asymptote is going for 3 units down. So, and let's see the whole thing, what we had in the beginning. So the parent function was y is equal to 3 times in 2x, and the transformation, it was f of x, but here I wrote with a different denotation with a y, and g of x is the purple function here, but I wrote with a y is equal to 3 times 2 in exponent 2x plus 1 minus 3. So in general, we can see all of this kind of transformation that occurred in the parent function. We had horizontal compression, we had horizontal translation, and we had vertical translation.